I'm Ben. This is my talk, Cloaked in Pixels, Concealing Payloads with Steganography. Before I get started, I just want to say thank you for giving me the opportunity to speak here today. The Southwest is very close to my heart. I was born and bred in Exeter. I lived in Exeter for 20 years. I've now moved a bit further north for a role. So I'm going to give a quick agenda of what this talk is going to entail. I'm going to start with an obligatory who am I, an introduction into myself and where I've got to where I am right now. I'm then going to introduce the concept of steganography. I'm going to highlight a few cases in all of history where it's been abused or used to achieve some objective. And then I'm going to get to the heart of this talk, which is a demo of a proof of concept steganographic shellcode encoder and runner. And then I'm going to switch seats, move to the blue team side, and show an analysis of a sample of malware which has been found in the wild used by a hacker and adversary to compromise a network. So yeah, let's begin. Who am I? I'm Ben, as I mentioned. I go by the online handle Polygon Ben. I've got a few blogs and a YouTube channel. I occasionally post content relating to CTF walkthroughs, malware analysis, and other miscellaneous security ideas um, or blue team stuff. In my professional role, I work as a senior SOC analyst at one of Accenture's SOCs. I do need to note this talk isn't associated with Accenture, and any opinions, views I say do not reflect those of my employer. Okay, so let us begin. So what is steganography? What is this talk about? The word itself, steganography, originates from the Greek words steganos and graphia, and this roughly translates to covered writing. So from the etymology of the word itself, we get a vague understanding of what steganography is. If you look at the definition, it is the practice of concealing information within another message or within a physical object with the intent of avoiding detection. This secret message wants to be hidden, and steganography is the act of hiding it within another message or object. So before we get into the how steganography is used by malware, let's just have a look at a few cases in history. And we're going to start off in approximately 500 BC. When I did my Googling, I believe this is the first ever recorded use of steganography, and it involves a Greek ruler called Histiaeus. He was the ruler of an area of land called Miletus, and he was held captive by a certain King Darius. And his brother Aristogras was looking after the city. He ruled Miletus while he was being held captive, and he needed to send a message to his brother Aristogras to inform him to start a revolution and to save Histiaeus from being held against his will. So he couldn't afford this message being intercepted. This was an important message he needed to send to Aristogras, but he couldn't afford the slave or the message being read and his plan failing. So he got his most trustworthy slave and he shaved the head of the slave, and he decided to tattoo the message to start this revolution, to start the revolt, and let the hair grow, let the slave's hair grow back, covering the tattooed message before sending him on his way. And if, let's say, the slave was intercepted, maybe the slave was searched, the message would be hidden as it's covered by his hair, as the message was tattooed on his head. So that's one particular case where steganography has been used, in this case to send a secret message. And if we go forward a few thousand years, we get to Nazi Germany, and Nazi spies smuggled espionage information using microdots. So what is a microdot? A microdot is a downsized image or photograph or a document onto the size of a dot. And when I say a microdot, it is genuinely the size. It can be as small as 1 millimeter in diameter. A fancy contraption of lenses is used to downsize a regular size document or photograph onto a benign object like a doll. So if, let's say, an intelligence officer did intercept one of these benign objects like a doll, they may look on the doll and there's no obvious signs of it containing espionage material. However, you wouldn't be able to see it because it's on a microdot. You'd have to use a microscope to actually view these microdots. But that is one method of how Nazi spies sort of transmitted espionage information, and it sits under the definition of steganography. So for the remainder of this talk, I'm going to be speaking about digital steganography. And this is a subset of steganography which really only considers hidden data and hidden text and hidden messages hidden within files rather than physical objects. So this begs the question, what file types can you use to hide data, images, messages within? And if you're creative enough, any file type is used or could be used to sort of transmit this secret information. However, in the wild and in the context of malware using digital steganography, we only see a smaller set of files frequently abused, and those are the ones I've listed here. So I want to try explain how digital steganography can be used and how it actually works. And this is going to get a little technical, but we'll see. So we need to take a step back before we can explain how steganography really works. I want to explain how we actually store images on computers. So you may have heard of the word pixel before. An image is an array of pixels, and this begs the question, what is a pixel? So a pixel is the smallest unit on a digital image that can be individually controlled and manipulated. And when I say individually controlled and manipulated, I mean, can we change the color of it? Can we control what color this pixel looks like? And how we define the color of an individual pixel, we use numbers, right? We use zeros and ones, we use binary. But for each pixel, there are three numbers. There are a number for the strength of the RGB components, the red, green, and blue components. And I've got an analogy for this. So as you see there, we've got what looks to be a photograph of Exeter Cathedral. Those with a keen eye will notice this is open in an Excel spreadsheet, so that is a little bit unusual. However, I'm going to play this video and we can see as we zoom in, this isn't just an image of Exeter Cathedral, it is actually an Excel spreadsheet. And when we zoom in far enough, like I've done here, you can see this no longer looks like Exeter Cathedral. This just looks like a spreadsheet made up of red, green, and blue cells. And this is an analogy for a pixel. I've highlighted 3 cells, Excel cells here, and we can see they consist of a RGB, a red, green, and blue component. And each of those cells have a number, and the number represents the strength of the corresponding RGB components. By the way, if you wanted to try this out yourself, you can visit this website. You can upload an image of your choice, and you can choose the image size, and it will automatically convert the image to a spreadsheet, and you can play around with it. So that's how I created that spreadsheet. Just to highlight this RGB pixel concept, what I've got here is another analogy. We've got 2 pixels. We've got 1 pixel on the left and 1 on the right. And we can see down here we've got the RGB components which make up the color of the pixel. And we've got the numbers down here. I've got the binary conversion, as you all know, computers use binary to store information, and I've got the decimal conversion. Decimal is what we count in, is the numbers we all know. For each RGB component, the maximum strength is 255, and the minimum strength is 0. What we can do, in this case, I've got 2 pixels, and I've got the far right-hand side bit. This is called the least significant bit highlighted. And for the red, the least significant bit is 0. For green, it's 1, and blue is 1 as well. What I can do is I can... give me a sec. I can modify this least significant bit and change this least significant bit from, in red's case, from a 0 to a 1 on the right hand side one here, and for green and blue we can change that from a 1 to a 0. And this changes the overall number of the RGB component, but the color isn't changed, and it is changed, but it's not noticeable. It's a very insignificant change. So we can modify these least significant bits, these far right hand side bits, without impacting the overall color. And that's the concept of least significant bit steganography. So we can encode our secret message or malware, in the context of malware, within the least significant bit of each of the RGB components of a pixel. You will notice, right, a pixel has a finite number of bits, a finite number of pixels. And for each pixel, you can encode 3 bits of data for each of the RGB components. So let's say the pixel is X bits wide and Y bits height. There is a maximum amount of data you can encode using this method, and that's just 3xy. So using this concept, I created a proof of concept script which takes advantage of this to encode malicious code, shell code into an image, into a benign image, such that when this image is written to disk, when it's scanned by antivirus, it will look totally fine. It won't flag up any hits, and it won't cause any issues. It looks like a benign image because it kind of is. You need the script, another script, to pull it out and decode that. I'm not going to explain this all in detail. I don't have enough time. However, if you would like to talk about this in future, I'm happy to speak on LinkedIn, or maybe organize another call with anyone who's interested, and we can go for it. I've also got a few blog posts which explain this sort of concept in detail. I'm going to put some links in the chat so anyone can, my LinkedIn and the blog post, so people can have a look at that. But I'm going to quickly go through this now. There's 2 scripts. They're Python scripts. One is used for doing the encoding. So you've got your image, your legitimate image, and you've got your sort of malicious code, your shell code which you want to encode in it. And the other one does the reverse. It takes the image and then it extracts that and runs it. So this is the script which encodes it. Like I said, I'm not going to explain this in detail, but you would run this on your sort of pen testing machine, your attacking machine, and this would allow you to encode the sort of malicious, the malicious code within an image. And then you've got the corresponding script which would be executed on your victim host, your target host. If you were pen testing, this would be on the one you were attacking. You would run it on this machine. And this is what the script looks like. Like I said, I'm not going to explain it now. However, I'm happy to go over it if anyone's interested, or you can read the blog posts. And I've got a quick live demo here. So in this example, on the right-hand side of my screen, I've got my Windows machine. I've got it open on a command prompt. And then on the left-hand side, I've got a Kali machine. This is a Linux machine which you can think, this could be the penetration testing box. It's a virtual machine, so you can think of it being as a completely separate computer. This could be somewhere else on a network. This could be on the internet somewhere. This could be on the other side of the planet. So what I'm going to do is I'm going to quickly run through this. I've got this recorded. I'm just going to show you Windows Defender is enabled. Real-time protection is on. I've got the antivirus enabled. And just to verify this, I'm just validating that the actual process on your computer, which is associated with the Windows Defender executable, is running. And I've also got another process, Hitman Pro, which is an antivirus associated with Sophos. On the left-hand side, I'm showing you I've got an image called newcastle.png. This is a legitimate image. This hasn't been modified. This is completely benign. And I've got the scripts encoder and runner, which I'm going to use to encode the malicious code within the image. And now on the attacking machine, on the left-hand side, I'm getting the local IP address because I'm going to create something called a reverse shell, which will allow me to gain remote access to the computer on the right-hand side. I'm then going to generate the shell code or generate the malicious code associated with that, which I'm then going to embed in the image. So the command I'm running there will generate the shell code. And once I've done that, you'll see once I run this, I need to also, I'm defining the L host, the listening host, this is the IP address of the Kali machine, and I'm also defining a port to listen on, so we can listen for incoming connections, such that when I run the script, I will get a callback, and I'll be able to basically get a reverse shell or remote access. So this is the shell code which I will use. You can think of shellcode just being computer code. That's what it is. In this case, it is malicious, but shellcode runs on everyone's machines. It's what our computers read and can understand. And I've saved this on my Windows host just to show you, just to generate this image. So I'm gonna run that v2 runner script in a second. So I'll run it with Python, and we can see it's asking me to input in the command line an image or file path of an image, and also the shell code which I want to embed within the image. And by the way, if I run over on time, please feel free to stop and jump in.
You're good on time at the moment.
Perfect. So I'm running the v2 encoder script, and it saved it. And now I've got this malicious image, and I'm going to open both of these images just to show you they are indistinguishable. They look identical, and you wouldn't realize the one on the right contains malware, which is capable of compromising your machine and giving a hacker or a pen tester complete remote access. So I'm just showing in the v2 runner script, I've set it's configured to read that malicious image. And you'll notice the image is called, the malicious one is POC Newcastle. I gave this talk at B-Sides Newcastle. So on the attacking machine, I'm now going to listen for remote connections. Like I said, I configured a port to listen on. I'm going to listen to it. And now on the Windows machine, I'm going to run this. And we can see all of a sudden on the left-hand side, I've gotten a shell. I can run Who Am I? I've got remote access to the Windows machine. Complete remote access. I've compromised my Windows host. And let me just skip ahead to there. I'm on the left-hand side. I'm going to run a command to create a directory on the right-hand side on my Windows host. And without touching the Windows host, you'll see all of a sudden this directory you have been pwned pops up. So that is just a quick proof of concept, an example of this particular script and how it can be used. This technique is used by malware to evade defenses, because when that image is downloaded to disk or it's written to disk, antivirus, if it scans it, will not be able to detect malicious content within it, because the method we used to encode it using least significant bit steganography. So why does this evade antivirus, and would it bypass EDR, endpoint detection and response? So antivirus is a traditional sort of security solution which works using signature-based detection. So when you download a file, your antivirus, whether it's Windows Defender, Sophos, maybe Norton, will scan it against a load of known malicious signatures. And if it fits one of those malicious signatures, it will fire and it will quarantine the file or do whatever. EDR, or endpoint detection and response, is much more advanced, and it uses behavioral-based detection. So instead of scanning the file, it will look what happens when you run the file or how it was written to disk. And EDR has a much better capability to sort of detect and sort of quarantine and remediate this specific technique. I haven't tested it on all EDRs, but I know, because how EDR works, it will be much better at sort of remediating and dealing with this type of malware. So now I'm going to switch seats to the blue team side, and I'm going to quickly walk through one case where it's been found in the wild. Steganography has been used in the wild as a way as a method to evade detection. And this case involves a phishing email. Most malware delivery techniques start with phishing. A user has been phished. In this case, there is a malicious document attached, and the document has a macro, which is an additional piece of code which will run and then will do further malicious actions. So we can actually have a look at what happens once the macro is run. And I've skipped a few steps here, but if anyone, like I said, wants me to go through this in further detail, just message me on LinkedIn. But once you download the Word document and you enable the macro, these commands will be run. And the command I'm pointing out here, the second one, is the curl command, and this will download a JPEG image from this www XML scheme format domain. And then there's a certutil command which will convert the JPEG to an exe. Certutil is actually a native Windows binary. It is on all your machines. It's used by sysadmins to deal with certificates, but it's legitimate. And the key point to notice here is it decodes the image and it converts it to an exe. So we can download this image ourselves and we can validate, look, this is an image. If you open this on your file system, you would see a photo of James Webb Telescope. You wouldn't suspect this contained malware. However, it does. We can actually open up this image and we can scroll through it and we can see a big chunk of text, which is actually base64 encoded. And we can use a tool called CyberChef, which is created by the folks at GCHQ to decode this. We can decode this base64 to actually extract the executable, which was embedded within the file, this msdll update.exe. And just to show you, we can upload this to VirusTotal. If you're not aware, VirusTotal is a website where you can upload files to scan them and to check whether they are malicious or not. And in this case, when we do this, we can see, look, this has got 53 out of 74 detections from various security vendors. It is definitely malicious. I do have a few things to mention, but I think I'm probably overrunning on time at this point. I'm not sure. Do I have any more?
You've got a couple of minutes because we've got you've got a couple more minutes just to round up if you like.
Okay, there's not much left. There are other scripts online for pen testers to use. One of them is this invoke PS image. This is a lot more elegant than mine, but this will allow you to embed a PowerShell script within an image, and then it will give you sort of a one-liner to run to sort of take that image, extract the malicious code, and then run it within memory, once again, sort of evading antivirus. And I've done this, for example, here. On the right-hand side, we've got the legitimate image, completely benign, and on the left-hand side, there is the malicious one, which contains malware. If you look up to it, you can see some minor discrepancies between the two images, but you still wouldn't suspect it's malicious. So to conclude, malware can abuse and frequently does abuse steganography as a technique to evade antivirus. However, it may struggle with hunting. It may struggle with EDR. EDR is much better at detecting these types of threats. If you did want advice on how to hunt for this activity within your environment, or to detect it within your own environment, once again, message me on LinkedIn. I'm more than happy to give any advice on how you can detect this and hunt for it, or explain it in further detail, as I was a bit cut on time.